All right, we're looking at practice problems. So we've already seen this example. This example shows the infinity norm for a particular signal. And again, I want to draw attention to the fact that we use the supremum, which is like the maximum, except the supremum holds when our value is obtained asymptotically and we never actually reach that value. So, all right, examples. All right, unit step function. So I'm going to look at various signals, and I want to look at the energies of those signals, the energy. So a unit step function is constant over all time, constant value of 1. The energy of that is infinite, because again, I square that, I take the integral, and the integral just keeps accumulating, and so I get infinite. Similarly for a sinusoid, if I square this and I integrate regardless of omega, regardless of phi, I'm going to get infinity. Okay, so basically you can think of it this way. For a signal to have finite energy, it eventually has to go to 0. If it doesn't go to 0, then you keep integrating, and that integral will go to infinity. So decaying exponential is another signal. So a signal that decays. Okay, I can go through and show that I have finite energy, and this is the actual energy value when I compute that integral, and it's finite for all a positive. As long as a is positive, this quantity will be strictly negative. I'm strictly finite. I can also have this spike function. So notice as t goes to 0, so notice that this function is not defined at 0. Actually, it's defined to be the value 0 at time 0. But anytime really close to 0, I can use this function, which is arbitrarily large. Depending on how close to 0 I get, I can make this signal as large as possible. That's why it's called a spike. It has infinite or very, 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 very large magnitudes. Okay, and but yet the energy in that, even though it has a very large magnitude, is bounded. Okay, the energy is 1 over root 2 for this signal. So I have a spike signal. All right, what about power of signal? So here is a unit step function. Its power is 1, so which is kind of interesting. It's basically the same magnitude. Okay, how about this sinusoid? Here's a sinusoid with some frequency omega, some phase phi. The power in this signal is 1/2, and it doesn't matter what omega is, and it doesn't matter what phi is, which is kind of interesting. Here we have this decaying exponential, so it's actually two-sided decaying exponential. Its power is 0. So it turns out for a signal, well, if I have a finite energy signal, so remember this signal actually had finite energy. For any finite energy signal, the power is 0. So basically, in order for a signal to have non-zero power, it must be a persistent signal. It must be a signal that goes on for infinity. Okay, so notice that those two signals have infinite energy. So those kinds of signals. The power of a periodic signal. So this is an example of a periodic signal, and I can go through and show that this periodic signal has power delta, and delta is the duty cycle of this signal. You can go through and calculate that. One norm. The unit step function has one norm, which is basically the absolute value, the integral of the absolute value. So again, with the step function, it just keeps going, and so the one norm just keeps integrating. Similarly, the sine wave is basically we first rectify it so that we have a full wave rectification. We integrate, and again we get infinity because again the signal just keeps on going, and so it keeps integrating. Decaying exponential. This decaying exponential is bounded in one norm, and this is the bound. And here's another spike. Okay, here's another spike. This spike. Again, as it's defined to be 0 at time 0, but arbitrarily close to 0, we have this function is defined, and so we have arbitrarily large values. And I can go through and show that the one norm for this signal is 2, but the 2 norm, the energy in the signal, is infinite. Okay, so this signal has infinite energy, even though it has finite 1 norm. Okay, so the two norms are not the same. Now here's a signal. it's multiplying a unit step function. So I have a decaying exponential, oscillating sinusoidal exponential for both of these terms. I can go through and compute the integral, and I can get a value, and I can see that in fact this is finite for all values of a and omega. Okay, I can see that the 2 norm squared is finite for all finite values of a and omega. Notice that if a is 0 or gets very close to 0, this quantity gets large because the a appears in the denominator there. So as far as 1 norm, if I take the signal and I evaluate the 1 norm of that signal, I can go through and do this calculation. So this integral is going to give me this value. This integral is going to give me this value. And so I can again see that the 1 norm is finite because, again, I have a decaying exponential that's multiplying these cosines. So I can go through and calculate that. For this signal, if I look at the infinity norm is the largest magnitude over all time of this vector, and I can see that the value is going to be 2. So that's what I get for the infinity norm of this signal. The RMS value for the signal I can go through and show as 0. The power of the signal, again, because it's a decaying signal, it's not a persistent signal, these are both 0. A specific case of this is so notice this is for any a and any omega. Here I've picked a specific a and a specific omega, and I can actually get specific values. Notice that I still get the same infinity norm, but these guys depend upon the values a and omega. Now, in terms of our Banach spaces, so we have L1, L2, and L infinity, and I showed this little diagram before. Now let's look at these L1 signals. So we're going to look at the case when we have L1 by itself, L1 that is with L2, and L1 that is with L infinity. And so these are examples of signals in each of those areas. So this signal, for example, is neither in L2 nor in L infinity, but it is in L1. This signal is in both L2 and L1, but it is not in L infinity. This signal is in all 3. So now looking at this space, I have 4 possibilities. And so I have these different signals that are in these different places. Notice that I don't have any signals that are in L infinity and in L1 that are not in L2. So that's kind of an interesting thing. Finally, in L infinity, looking at the L infinity spaces, here's a signal that's in L infinity, but it's not in L1 or in L2. This signal is in L infinity and L2, but not L1. And this signal is in all 3. So that's an example of the signal spaces and elements in those spaces.